I Googled what's the most toxic substance known to man, and what popped up is that I don't know how to pronounce it. Does anybody know how to pronounce that? All right, but it's really, really toxic. So this lady wants to kill her husband. Doesn't want to get caught either. So such a small amount, 90 grams distributed through your body only metabolizes a few small percent of that. I don't know if there's a machine on the planet that could detect it. So anyway, but there probably is, because she's a scientist and they check her orders, and who knows, she probably won't get away with it. But anyway, so she wants to see if she put in that minimum amount, so she does this fancy titration. And pH is pretty sensitive. I don't know if it'd be sensitive enough to do this titration, but you know, and she got it all to work. But the point is this is pretty cheap stuff to set up. And to do a very solid scientific analysis, I mean, those numbers are good. You don't need to buy a $70,000 GC mass spec to do this. It'd be nice, but you don't need it. So she gets her nice little pH plot. And maybe you've done a titration in general chemistry and you get these types of titration curves. But what if she would have got something like this? Destiny, do you think she would have screwed up then? Or is this an actual valid result? Can a titration curve look like that? All right. And notice how it starts really low in pH. So it's probably an acid. Starts really low. And they're adding base, right? So the acid's reacting with the base. And it looks like it goes up. Something reacts, but then something reacts again. That's all it means, is that whatever this compound was had how many acidic protons, how many acidic hydrogens on it? 2. It's diprotic. It's a diprotic acid she just titrated. That's all this really means. Okay. So with titrations, a volumetric analysis is what this is. Okay. So I've got it here. So I want to titrate so many mils of an unknown concentration of nitric acid. So this is exactly 265 milliliters. Right? 265 milliliters of an unknown concentration of nitric acid with 2.1 molar NaOH. Okay. Oh, I got the wrong. Change this to 2.1. Okay, this says 2.1. Okay, there's my 2.1 molar NaOH. So the question really is 265 milliliters of, we don't know concentration of HNO3 equals, this is what we need to find, that many mils of 2.1 molar NaOH. When they do titrations, they like setting this mole equivalency thing up. And that's really the point of equivalence point, is that those moles are exactly the same at the equivalence point. That's why they like the word equivalence point. So the moles of HNO3 exactly equals the moles of NaOH. Okay. So it's kind of a theoretical thing, but that's okay. So how do I do this? I got a couple arrows here, like this arrow. What do I put in? What's this doohickey called? The barrette. So what do I put in the barrette if I want to solve this question? Which is, good? The NaOH. Right. So, Javier, you're taller than I am. Right? So you can dump that in there for me? Just be careful. Right? Okay. And then I need, oh, well then if that's the NaOH, I didn't label that. So go ahead and do that while we're filling this stuff in here. NaOH goes here. And what goes in here? Our solution that we're titrating, right? Well, yeah, let's fill it up to here somewhere if you can. Right? There you go. See, he doesn't even need a step ladder. Isn't that nice? Well, that's good. That's good enough, right? Okay, and then our unknown solution here. Thank you, sir. Okay. So he's got it started for us. So Brad, come on up. Okay. Now, how do we do the rest of this? Do we need this stuff? Right? What's the indicator do? They step on this side. Yeah, so you know when to stop adding this stuff, right? Now, a common mistake that hopefully you won't do in lab is, so Brad, go ahead and get started on this, right? So he's going to put, yeah, I can get, oh, he grabbed the indicator already. He knows what he's doing, right?
Do we know how many drops?
Yeah, it really doesn't matter, right? Now, there is something called indicator error. So you put a few drops in there, okay? And indicator error is, number one, you could use the wrong indicator. These indicators, they just change color. You just stir it up all nice. They change color at a certain pH, at their pKa, really. So it depends on, and we'll get into this a lot deeper, only do you use phenolphthalein when you're adding a strong acid and a strong base. If you end up at the equivalence point with a weak base or a weak acid, your pH isn't 7, it's somewhere else. So you have to use a different indicator. Another indicator error is, like he asked how many drops to use. So you should actually use the same number of drops every single time when you're going through the lab, right? Okay, now before we get started, we need to do, I see 2 things. All right, because he wants to open it up. But if he starts adding right now, well, first we better write down this thing, right? So can you read, what does that say? What's that volume?
58.
Can you read the decimal part?
He's got real good right on the meniscus, right on the bottom.
Oh, 58.0, perfect. Okay. That's where we're starting. Now, this is the other part I wanted to catch. There are 2 things. He wrote it down, but also, see this part? The part down here. You remember Javier just filled it up, but we didn't fill up this part. So if he starts titrating, right, he's going to fill up this first, and then it's going to go in here. Ah, you just screwed it up, right? So we got to purge it or fill this up first, and then we'll get started. So I just do it over the do it over the drain. Yeah, do it back in there. That's a good idea. That's a great idea. Just do that. All right. Ugh. All right. Now we have to reread the number again. All right. So it's not 59.0 milliliters? Okay, perfect. Okay, now we should be good to go. So we can go ahead and just dump some in. Let's do it fast, right? Remember there's this fast. So just stir it as it's going. They have this idea that, remember you've heard preliminary titration, and then, which is kind of what we're doing here. They believe it's faster, which probably is a good idea because we have no idea how much to add. So you sit in there and you get a rough idea. Dump it in really fast. Oh, it changed color and stayed that way around after we added like 30 milliliters. And then the next go around, add 28. And then the last part you do really slow, right? Ah, great. Yeah. See, so it is kind of dark. He's right. Went over a little bit, but it's not that far off, right? So now we know it's what? Oh, it's right on there again. Our math is easy. What is it?
23.
23. There's our final. Thank you, Bradley.
Thank you.
Yeah. All right. So now we know it's roughly 23. So if you want to do it again, just be much more careful when you get around, right? What is that? 9 minus 3 is 6. 36. Around 36 milliliters. Okay. So how about endpoint? We haven't talked about that one. What's the difference between endpoint and equivalence point? Zach, what's the difference?
Equivalence point, it's supposed to be that for every OH, there's an H. It's balanced.
Yeah.
pH-wise. Endpoint, it's in one direction rather than, right?
Close. You're talking about OH and stuff for equivalence point.
Right.
Theoretical. In theory, if we knew what this concentration was, we could calculate the exact volume of NaOH that's necessary. That's the equivalence point. Endpoint is the actual, remember Brad said, oh, I added too much. Endpoint is this guy, when he changes color. When you think, oh, I better stop adding here. Okay. So that's kind of kind of the difference. End point is observed, the equivalence point is theoretical. Okay.
So the difference between the indicators is the pH that
We need to get a little bit further, but we'll see it. We'll see it. And we have to pick different indicators for different titrations. But just for now, just realize, yeah, you should be picking a different indicator for different types of titrations, depending on where you end up. And we'll just leave it at that for now. But let's finish our answer here. We added 36 mils. What will our constant? Oh, we can write the 36 in here. What is our concentration of NaOH? Or it's not concentration of NaOH. What is our concentration of nitric acid? How would you get it? I don't think MIVI, MFBF won't work. I don't think so. Well, it might work. It might work because it's a 1-to-1 ratio. It's dangerous. It's dangerous. But MIVI with MFBF would work, I think, in this. I think it would because they're 1-to-1 ratios. But it's a dangerous game. Yeah, it's a dangerous game. So what I would do it this way. This is what I suggest. The question mark molar nitric acid is really what over what? What are the units of molarity? Moles. Yeah, moles of, in this case, moles of solute, but moles of molarity of HNO3, so it would be moles of HNO3 all over liters of solution, or that liters of that HNO3 solution. So what's the liters of HNO3 solution? The 265. Very good. That's the 0.265 liters. All right. The moles of HNO3 we need to get. All right, so how are we going to find that?
You take the 36 milliliters.
There you go. Get the 30. Yeah. And then use the mole bridge to get it into moles of HNO3. And since the mole bridge is 1-to-1, we could have got by with the dilution equation. But notice when it's not 1-to-1, it's not going to be when we go further down in here. So it's dangerous. I would start with on a problem like this, because it works every time.
So if we're positive it's 1-to-1, then we can use that density
It's-
and not mess it up or anything like that?
I mean, I'm not going to stop you, but it just conceptually doesn't help me. So I don't like to memorize special cases for special things. I'd rather just follow the logic and do it the same way every time. But yeah, I like uniformity. So then you said times the concentration of the NaOH, right? Because I used 36 mils of it, 2.1 moles of NaOH, and a liter of that NaOH, and the ratio 1-to-1. Okay, 0.036 times 2.1 is about 0.07 something something. .0756. So that's what we'll put in up on top. Divide it by 0.265 liters, about 0.29 molar is our final answer. Okay.
How will you know when it's a different mole bridge? Will it be like?
Oh, you kind of just got. Oh, here's a good one. You're going to see this a lot. What if you had calcium carbonate and HCl? And that's coming up. That's kind of cheating because that's coming up. Could pick something else, but it'll work. Right? This is how many negatives on the carbonate? -2. So if you react with just one H, you have HCO3. It's going to react with two H's, H2CO3. It's kind of weird. Usually we like to, what drives a reaction? Usually solids, right? We like to form solids. Why does that work? Because it kicks out a solution. It's Le Chatelier's principle. And what's really weird is a weak acid is just like a solid. You're forming it. It's getting it out of solution. And it won't come back. It's weak acid, so it's not going to have a reverse reaction. So you can form these weak acids. H3PO4 would have been another, or sorry, sodium phosphate would have been another example, right?
Question for you.
Tribasic. So this ratio would be 3 to 1, right? Okay, that'd be 3 to 1. So you keep forming these weak acids.
So you're just looking at the charge of the anion?
Pretty much that's all I'm doing. But I'm thinking in my head, oh, I'm forming, oh, that's somebody's conjugate base. So I can form this. Oh, but that's somebody's conjugate base. So I can form this. But that's somebody's conjugate base. So I can form this. And I can keep playing that game for anything that's a weak acid. It'll always work. You just can't form what types of acids ever? Strong. You can't do that. You can't play that game with strong acids. But that will always work. That's why I'm used to seeing this as, oh, that's just looking at the sodium phosphate. I'll say that's a 3 to 1 ratio of HCl to phosphate. You'd have to react 3 moles of HCl for every 1 mole of phosphate. Yep. And then they could make the game even more complicated. I don't know if they do this in the homework. I doubt it, but it'd be good if they did. Now that ratio wouldn't be 3 to 1. It would be 2 to 1. Right? Okay, so I think you got the idea. Spectrum photometric titration, I wrote all over it, but pretty much all you do is just have color. So one of your reactants, right, you're reacting something with something else, and you're getting a product. And your titration, right? One of them's in the breath, the other one's in the beaker. Something just has to be changing color when they react, or forming a color when it reacts. And you're just monitoring that as it happens. So, but if nothing does, then you can't do a spectrophotometric titration. Okay. Okay. So here's some questions. And the book may want you to handle titration questions like this. But I don't think we should. But they may want you to handle titration questions like this, setting up these mole equivalencies. And it's a nice concept. Right? How many milliliters of Ki are needed to react with 40 mils of this mercury 2 nitrate? So moles of Ki has to equal moles of mercury 2 nitrate. But that's not how I'm going to approach it in class, and I hope I don't confuse you, but that's not how we've been working all these questions. Right? We're after what? Mils of Ki. So we just handle it, write down all of our conversion factors, like with molarity, and we just handle it the way we have been handling it. And just realize, oh, we have a whole bunch more ratios to worry about. Conversion factors, our mole bridges. We can convert from one compound to the other. Okay, so I think it's neater that way. I think it's more logical. That's how we've been handling it. So where would you start on something like this? Mariella, where would you start if we want to approach it the way we have been approaching these types of problems in the past? Yes. Yes, thank you. Right? Like 1 mole, she said, rewrite these molarities. 1 mole of Ki over a liter of solution. Right? They want to know how many mils of Ki. What else could you write, Sochi? If you want to spill out all of our, that we can, of our conversion factors. The 0.04 moles of that Hg2 plus 2 nitrate. Okay. Oh, here's a question for you. Caroline, let me ask you this. Oh, isn't it nice that they gave us the concentration of this stuff, right? But it's not even in our reaction. Here's our reaction. Or is it? assuming something. That you see this. They're assuming that you see this. What are they assuming that they expect you to see? You see it? You want to see what I'm driving at? Nitrate totally dissolves. All nitrates dissolve. I've been harping this whole time on which group? Group 1, where, yeah, don't even ignore, just ignore sodium, lithium, potassium. Well, there's also the nitrates. Ignore nitrates. It allows you to get cations in solution. Okay? It's hard to get that mercury 2 in solution without a nitrate. I don't know what else you could use. You have to look at the solubility rule. Okay? Oh, if you want to do the dilution equation, it won't work for this one. And I'm positive because you have to use the mole bridge. The ratio isn't 1-to-1. So that's why it's dangerous to use this MIVI thing. That's really only for dilutions.
You can't like factor that into the MIVI?
You could, yeah. You can fudge it. You can fudge it. But if that helps you, there's fudge it because MIVI equals MFVF is a dilution equation. But if you know what you're doing, if you keep track of it, oh, I'm off by a factor of 2. Either I have to multiply or divide, right? To me, that's called fudging it. And that works, right? And just have to write down why you did what you did. I wouldn't argue with it. Okay, so where do we start? Alyssa, where would you start?
I would split the liters of solution.
With the Ki one. Right, she picked the right solution. They want to know how many mils of that Ki solution. So this is the solution they're after. So that's the one she flipped. Very good. Okay, then what? Ashley. Okay, how would you do it? Good. She wants to get rid of these moles of Ki. If you do molar mass, you end up in grams of Ki, which is possible, but how would you get rid of the grams of Ki? Not molar mass. It would be mole bridge is what you meant, because you want to bring in the Hg. Exactly. So Hg2 plus 2. So yeah, so what's in front of the Ki? Yeah, excellent. Thank you. That's a 2. Notice how, yeah, again with the iodide in the reaction. They expect you to see this solution as I negative. They don't expect you to see the K at all. You're supposed to block that out mentally. Well, that's 1 molar iodide. Okay. Keep going. Jesus. Oh, I didn't put a 1 down here, did I? Okay, keep going. All right. Yeah, so they have to cancel. Yeah. Don't forget these guys. All right, this is the one we're messing with, right? So on the bottom would be liters of solution. So we'll have the 0.04 on top and the liters of solution. All right. Jenny? It looks weird, doesn't it? Liters of solution on top and bottom. Looks like they all can. But remember, these are different solutions. Yes, because we might want to write more words on here. This is liters of the mercury 2 plus 2 solution. This is of the Ki solution. Otherwise, it looks like they cancel. So it will be the 0.04 liters of the mercury 2 plus 2 solution. Might look better. Then our answer is in liters. Do they care? Oh, they care. Shoot. All right, so a liter, 1,000. Whoop, wrong way around. Liters have to cancel. Okay. So 2 times 0.04 times 0.04 times 1,000. About 3.2. Okay, about 3.2. Okay. Limestone mainly consists of the mineral calcite, or calcium carbonate. The carbon content of 0.5413 grams of powdered limestone was measured by suspending the powder in water. Why didn't they use the word dissolving? Because it's not soluble, right? I mean, a little bit will dissolve. We know solubility, a little tiny bit will dissolve, but you're just going to have this powdery mess in there, right? And you can shake it as hard as you want. It's just going to stay there and be a cloudy mess. So that's why they use the word suspending in water. Adding 10 mils of 1.396 molar HCl and heating to dissolve the solid and expel CO2. So the excess acid required 39.96. Now this is where it's a real applicable question, because you add this solid, the stuff doesn't dissolve. So if you want to just imagine if you want to do this careful and do a titration, right? What they did, they literally dumped in I don't know why they picked such a weird number, 39.96. Just dump it in, right? They wanted excess. They dumped in a lot, just a known amount. Because just imagine if you do it the other way and titrate it. You add a little bit. Oh, shit. It's a powder in there. It's going to take forever, right? And it'll work, but it's going to take a long time. Versus this way, add a whole bunch of this. What did they do? They added 10 mils of 1.396 molar HCl. Oh, there it is. It is an exact amount. Sorry. They did add a whole lot, an exact amount of HCl, right? They just literally dumped it in. It's gone. It's all dissolved. It all reacted up. So some of that HCl reacted with this calcium carbonate. The rest of it is excess, and it reacted with this. Right? So much easier than sitting there trying to titrate a powdered solution. Just dump in a lot of acid, know the amount, and then titrate your excess. Because it's so easy to titrate HCl and NaOH. So they're moles of HCl. If you don't see it, they're moles of HCl, right? That they added will be the moles of HCl that reacted with the calcium carbonate, and the rest reacted with the NaOH. Does that make sense? Okay. We're going to do that in lab too. I think we did a calculation like this. Okay. Makes sense? See why they did what they did? So now we just have to figure it out. Okay. And in figuring it out, I like to start with the answer because it guides everything I'm doing, right? This is just a concept from reading the question. Hopefully you can get this out of reading the question. That the total moles of HCl, the moles of HCl reacted with calcium carbonate, and the rest that was excess reacted with NaOH. So what they want is the weight percent. What they want is the weight percent of calcite, calcium carbonate, and limestone. So, okay, weight percent would be the grams of what over the grams of what? The grams of the, they call it calcite. Yeah, grams solute, but calcite, it's also what formula in our reaction? The calcium carbonate. The grams of the calcium carbonate divided by the grams of what times 100?
The solution?
The solution. Or in this case, the solution is a powdered solid, right? Do we use all 0.5413 grams? Or did they take a little portion, do like we did in lab? Or did they titrate they react with all 0.5413 grams?
All of it.
All of it, right? According to this, it looks like all of it. So you put down the whole number down here. Grams of the solid unknown, 0.5413. So we just have to get these grams of calcium carbonate. Okay? So Albert, looking at the writing I have in purple here, which one of these, if we knew it, could we use to get the grams of calcium carbonate? Which one, if we knew it, could we use to get the grams of calcium carbonate? The moles of HCl that reacted with calcium carbonate. If we do this, right? If you knew the moles of HCl that react with calcium carbonate, use the mole bridge to get it into moles of calcium carbonate, use molar mass to get it into grams of calcium carbonate, you're there. This is the one you need. We want this one, right? And then we'll convert it to grams of calcium carbonate. And then we'll put it in up here. Well, this is just like any other math equation you've reached. If you have one equation, they have to give you everything but one answer. If we're after this one, you have to know moles of HCl. You have to know the other one. That's without even reading the question. It has to be in there. Otherwise, the problem can't be solved. So the total moles of HCl has to be in the question. The moles of HCl that reacted with NaOH has to be in the question. Do you see one of those? Jamie, do you see one of them? Yeah. There it is. Which one is that one? Good. Which one is this? Yeah. Right? That's the total moles of HCl. Right on the left? Sorry. Oh, sorry. Right? Yeah, I'm running out of that one. Okay. So the moles of HCl that react with NaOH must be this one. But that's NaOH. Does it matter? What's the mole bridge of NaOH to HCl? 1 to 1. And that's another one thing that they're going to expect you to understand. That they expect you to see H plus OH minus makes water. 1 to 1 reaction. And they expect you to see, oh, any strong acid, any strong base, 1 to 1 makes water. They don't care about those spectator ions like chloride, like nitrate, right? Like potassium or sodium on the base. See if you can get it. Get these moles of HCl, get those moles of HCl that reacted with NaOH, put them into our expression, figure out the moles of HCl that react with the calcium carbonate, convert it to grams of calcium carbonate, throw it in our weight percent, see if you can get it. Okay? And if I lost you, just ask. It's nice getting warm in here, isn't it?
Why do we care about the moles of HCl and the moles of NaOH if we're just trying to find grams?
Well, 'cause how else are you going to get the grams of the calcium carbonate? Because it's just hidden. It's hidden in the data. Because we know that this HCl that we added yeah, we get all these little bubbles coming off this carbon dioxide. This calcium carbonate's in there. How do you figure out how much is there? Well, they just added a bunch of HCl. And then we titrated what was left over. But all the HCl we added, we didn't titrate at the end because some of it is less, right? That the 39.96 mils of 0.1004 molar NaOH, that's a small number of moles of HCl that actually reacted. So most of it actually went into reacting with that calcium carbonate. So the only way to get the grams of calcium carbonate is to really work backwards. We need to, I started with the weight percent just to show that we needed it, and then get the moles of calcium carbonate from the moles of HCl that reacted. And the only way to get that is to recognize the total moles of HCl and the excess. There's no shortcut.
So once we've done the moles of HCl, we do the mole bridge to get into moles of CaCO3.
So you're talking about which one? This one? This one, you just get total moles of HCl and put that number here.
Oh, but yeah, I'm talking about that one, sorry.
Yeah, this one. Yeah, you're going to have to use the mole bridge to get it into...
You get moles of HCl first. So.
Yeah, start with moles of HCl, and then 2 moles of H for every 1 mole of calcium carbonate.
And then after that...
Then molar mass of calcium carbonate.
And that's going to be that.
Yep.
Dr. Smith,
Yep.
when you, okay, so we would get the molar bridge with HCl to find the CaCO3?
No. Hang on. No, you need to get... Let's get moles of HCl. You skipped a step, I think. According, from what I see that you did. Let's get the total moles of HCl. Right? That's from that information way up on top. 0.01 liters times 1.396 moles of HCl per liter. So that's what? 0.01. Right? And then get the moles of HCl that reacted with the NaOH. .96 milliliters, or 0.03936 liters times 0.3936. Thank you. It's 2 nines. Thank you. So then we can put those numbers in. I'd probably start somewhere else, right? Go down here. Okay. Did you get somewhere around like 9.9 times 10 to the negative 3 for the moles of H that reacted with the calcium carbonate? Did anybody get that? Right? So that's what you need to convert all the way to grams of calcium carbonate.
The 0.01396 moles of H plus.
That's the total.
And that, you got that for 10 milliliters.
Yes. Yep.
And then that's the total.
And then the other amount, this amount.
Okay, wait, so where's the calculation for the CaCO3?
Okay, I didn't do that.
Oh, okay.
So 9.9. I can make a different color. Let's make it so you can see it. So 9.948 times 10 to the negative 3 moles of H plus 2 moles of H plus for every 1 mole of calcium carbonate. And then in a mole of calcium carbonate, I have the molar mass of calcium carbonate. What's the molar mass of calcium carbonate?
So 100 grams.
Is it already nailed 100?
It's like
0.08. Okay. So we're about 0.498 or so.
Yeah, I tried to do some stuff.
All right. So hopefully you get around 0.498. Throw that in up top. Divide it by 0.5413 times 100, about 92%. Is our final answer. Okay. So have a good weekend. Come by. I'll be glad to work these out with you. Give them a shot.